Hello, in today's lecture, we will learn about how we can use simple neural network structures to solve linear problem. So basically, the lecture will comprise of the introduction about the internal architectures, about the simple neurons, and then later on, how we can configure or tune the neurons in order to converge with the given dataset. So basically, the lecture will consist of the five main parts. So the first one is the introduction to the macular neuron, which is one of the simplest architectures of the artificial neuron. And then second one, I will give a brief overview about four main algorithms that can be used in order to configure the neuron. So basically, configure the neurons means that we tune in term of the weight of the neuron that able to solve or able to converge with the given input data set. So let's get started. So the first part, we will learn about the configuration or internal structures of the macular neuron. So in a simple way, so this is the basic structures of the McAleep's neurons, in which I think you are quite aware about the set of input here. And then later on we have the set of the wake here, which is in between of the input and the neuron. And then basically for every of the neuron will be consist of the two main parts. The left side is actually the summation part, and then whereas the right side will be the activation part. So for the macular neuron, so this is just a simple structure that use the binary activation signals. So basically, in terms of the output of this part is that it will trigger if the wake is positive, and then it will be not trigger if otherwise. So in general, for this type of the neuron, you can say that it will be more or less in terms of the simple threshold function that will be only trigger, or we call that thing as the fired, when the value will be higher than a specific given threshold. So in general, for the first macular neuron, so it is the wake, which is the synapse information here, is actually assigned rather than adapted. So means that what we need to do the heuristic search, we need to empirically select the values so that the model can be used in order to solve the given input data set. So for this type of the neuron, so in general for the implementation, it only used for the hardware such as relays and resistors. So to gain some sort of the understanding about how we can utilize the simple single neuron in order to solve this problem, in order to solve the given problem, let's say we have this kind of sample set in which class A is the green data set, whereas the class B is the red data set. So if we wish to solve this particular cluster, or we want to separate, or we want to create the border to able to separate the cluster well, so we can use the neuron model, which is in this case x1 and x2 is the input, and then w1 w2 is the weight, and then b is the bias. So what we can do for this particular case, the neuron can be assumed that you have a ruler that can be used in order to spread this data well. So you can actually locate the ruler in any area in between of this space, as long as it's able to separate the data well. But usually in designing the proper border or the cluster border, so it will be better that we're able to locate the line in which the separation between two clusters will be maximal. So the configuration of this line will be directly related to the value of W1, W2, and B, in which equation of this line will be this part, in which the equation for this line is x1 W1 plus x2 W2 plus B equal to 0. So if you change the value of W, either the W1 or W2 or B, so in general we can generate a different type of line in order to spread the data well. So basically for the single neuron, it can be used in order to solve only linear problem. Why linear problem? Because you only have some single ruler. So if you wish, you can put the ruler in any location, but you have only single ruler. So in a situation that you deal with the nonlinear, means that you need more than one ruler in order to solve that particular problem. So for that particular case, we cannot use the single neuron in order to solve this problem. So in general, for the linear problem, it can be used in order to solve the n, which is this is the linear problem, or problem, for instance. So this is the linear problem, but not the XOR problem. So along the way, I will explain to you why the single neuron cannot be used in order to solve the nonlinear problem. So basically, I just want to emphasize on one of the important parameters in which the different type of value here is very crucial to be tuned to ensure that we're able to generate the line, the separator line, that able to optimally differentiate between these two type of cluster. So this is the role of the learning rule, in which the aim of the learning rules is to configure or to tune the parameters of the wake and also the bias, these two type of parameters, in order to ensure that it can be used in order to solve or in order to separate the given data set. So basically, you use different type of data set, so there is some possibilities that the value of wake and bias will be different. So this is some sort of the simple explanation of the learning rule is designed by choosing the appropriate value of wake so that the actual value has the desired output. So in this particular case, we can say that actual minus the desire supposed to be equal to 0, in which we don't have any error. So in the later chapter, I will show you how we're able to perform the training session in order to estimate or to predict the value of W and B that able to converge with the given data set. So this is some sort of the four basic methods that can be used in order to tune or configure our model. So the first one is based on the analytical. So the second one is based on the Hebbian, third one is the perceptron, and then the final one is based on the Adeline learning rule. So Adeline is actually the short form for adaptive linear element. So one thing that you should note that analytical method will be based on the empirical method. Means that in a sample elementum is more on the try and error, what is the optimal value that can be utilized based on the given some sort of the function, constraint function. So the other three methods, the Hebbian, perceptron, and the Adeline, will be based on the iterative method. Iterative means that it will converge in every step that you feed the new data set, and then it will be something like it can be repeated if the performance is not satisfied. So in the next part, I will cover the first method, which is how we can tune or configure the wake by using the analytical method. So for the analytical method, this is the empirical way, as I mentioned previously. This is the heuristic empirical way in order to determine the neuron weights and the bias value. And then analytical will be consists of, I just summary, this method will be comprises of the two main steps only. So the first step is to construct the constraint functions. So the constraint functions will be constructed based on the given input sample. So let's say if you have 4 samples, so in this case you will have 4 constraint functions. So let's say you have 10 samples, so it means that for that particular situation you will have 10 constraint functions. So the second step is selection of weights and a bias value that satisfied with the constructed constraint functions. So the second step means that you have, let's say for this case, you will have the 4 constraint function, and then later on we need to find what is the value of weight and bias that able to satisfy the constructed all these 4 constraint function. So I will show you the details based on this simple example. So for this particular case, we have this type of the sample. So the sample is the two-dimension input in which we have x1, x2, and d is the output. So in this case, 0, 0 is 0, 0, 1, 0, 1, 0, 0, 1, 1 is 1. So this is actually the end problem. So the question is that what is the value of W1, W2, and B, and also the theta. They're able to separate or distinguish this data well. So if I try to plot this type of sample, let's say x2 is the y-axis and then x1 is the x-axis. So for this particular case, let's say we put here is 0 and then this is 1, the same thing here, 0, 1. So for the first sample here, 0, 0 will be 0. So for this case, let me change the color first. Okay, for the first samples here, so 0, 0 will be 0. The second sample 0, 1 will be 0. So means that for this case x1 is 0, x2 is 1. The third one x1 is 1 and then x2 is 0. So it will be here. And then the final one 1, 1. So in this case 1, 1 is here. So I just put, let's say, x in order to represent the fourth sample here. So so this is the scatter plot of this type of the sample. So you can estimate that this will be the optimal borderline in order to separate this data well. But the issue is that how we able to find this the function of the line by using the analytical method. So to show you in details, let me open up my whiteboard so that we can do the calculation based on this example. So as I mentioned previously, so in terms of the analytical methods, we will have 2 steps. So the first step is to construct the constraint function, and then second one is the optimal value of weight and bias that able to satisfy with respect to the constraint function. So let's start with the first step. This is the first step, step 1. So the step 1, we want to construct the constraint function based on the given input sample. So let's say if I give some tagging here, let's say this is A, B, C, D, that represent the first row, second row, third row, and etc. So the first row, so let's construct our first constraint function. So I just put here an A. So the constraint function for this thing. So how we able to construct the constraint function is just simply we fed the value here 0 0 and then put the output D as 0. So in this case, if we put our input here is 0 0. So what is the value of theta based on the given value of D? So for this case, if we put a 0 0 here, so the first line here, the output will be 0, and then the same thing for the second line will be 0 plus this is B. Okay. So based on the given target here, so since the value of D is equal to 0, so for this particular case, we can say that the output of this part will be less than theta because of the output of target is equal to 0. So this is the means that the neuron will not be fired for the first case. So let's move on to the second part, which is part B. So for the part B, we will do the same things, means that for this case, x2 will be equal to 1. So let's say we plug in the same thing. So the first part will be equal to 0, and then the second one here will be equal to w2, and then the same thing plus b. So we look at the target for the second sample. So since the value is 0, so we know that the neuron is not triggered. So we can say that in this case, the value will be less than theta. So you just need to remember whatever, if the value here is equal to 0, means that it will be less than theta, means that it will be not triggered. Whereas if the value is 1, so for that particular case, the value of the input, summation of the input will be higher than the threshold, so that it will be triggered or it will be fire up. So we plot the third sample, which is sample C. So for the sample C, the value will be 1 0. So let's say I just change the value. So sample C, it will be 1, and then this thing will be 0. So the same thing, so the first one will be w1 plus 0, then plus b. So if we look at the output for the target here, so means that it will be less than theta, since it is not fire up. And then finally we move on to the next sample, which is the sample D. So for the case of the sample D, for this case is actually we have the value of 1 and then 1 here. So for this particular case, for the sample D, means that W1 plus W2 plus B. So for this case, since the target is equal to 1, so we can say that this part will be fire up, so it will be higher or equal to theta. So once we finish construct the constraint function for every sample, so for this case 4 samples A, B, C and D, so we can move on to the next step, which is the step 2. So step 2 means that we try to find what is the value of theta, what is the value of weight and B that able to fulfill with this type of problem. So in this case, it will be more on try and error. So let's say to make the things simple. So let's say we will start with the more simplest type of the equation, and then we will move to the next equation that will be more complicated. So let's say for this case, if this is more on try and error, so means that you will have infinity solution. So maybe you pick up the different values and then your solution will be different with your friend. So it will be common for the analytical method. So let's say for this case, I select if theta equal to 2. Okay. So if I set theta will be equal to 2. So in order to satisfy the first constraint function, so b will be less than theta. So in this case, b must be less than 2. So let's say I pick one of the value. Let's say b equal to 1 for this case. So we're able to fulfill the first constraint function. So this is settled. So let's move on to the second constraint function. W2 plus B will be less than 2. So in this case, since W2 is equal to, since B will be equal to 1, B equal to 1, and then theta will be equal to 2. So if we wish to get the value of W2 for this case, so W2 must be less than 1 in order to satisfy the given constraint here. So let's say I just pick up W2 maybe equal to 0.3, which is it will be less than 2. Since if you add up here, so W2 0.3 plus 1, which is 1.3, will be less than 2. So the second constraint function is satisfied. Then we move on to the next constraint function. In this case, W1 plus B will be less than theta. So theta will be equal to 2, B equal to 1. So the same thing we can say we select the W1 value will be the same with W2. Since the constraint function is more or less will be the same. And then we try to move on to the next part, which is the constraint function of B. So for this particular case, W1 plus W2 plus B must be equal or higher than theta. So in this case, if we select W1 0.3, W2 0.3 plus B, let's say B is 1, so you have 1.6. So for this particular case, 1.6 is less than theta. So means that we enable to fulfill the constraint function number 4. So under this situation, what you need to do, you need to change the value here. They're able to satisfy the constraint function D. So in this case, I can simply change the value of W1 and W2 in order to ensure that it will be fulfill the constraint function number D. So what I can do is that if I change the value of the constraint function B and C, if I increase the value, so in this case I put the different color so that we know that this is the new value that we have tuned. So let's say I select the value of 0.6 for W2 and then 0.6 for W1. So if I put here 0.6 plus 1 is still less than 2. The same thing with the constraint function C. 0.6 plus 1 will be less than 2. So if I plug in all the value of this part, so I put the blue number. So this is 0.6 plus 0.6. This thing will be 1. So we can say that this is 2.2. So means that if we check the constraint function D, so means that 2.2 will be higher and equal to 2. So we are able to satisfy all the given constraint function. So in this situation, we can say that by using the analytical method, this will be the optimal value that can be utilized in order to ensure the neuron will be converged with respect to this data set. So what we can do next is that we can actually cross-check the performance of our new value. So how we can do that thing? So we can just simply plug in all the given value. So in this case, this is x1, this is x2, and then this is the value of bias. So we just plug in all the value here. So this is the summation in terms of the theta. We say that theta will be equal to 2, and then this value will be 0.6, this thing the same thing 0.6, and then for the bias will be equal to 1. So we can cross check the performance by using the same. I just replicate the previous sample configuration, in which this thing will be x1, x2, and then this thing will be d, and let's say this is our verifier. So I just copy the previous sample configuration 1 0 0 and then 1 1 1, and then we just verify, just put here v, which is the output based on the constructed optimal value here. So let's say for this case, for the first example, so 0 0 0 0, so you will have the value here will be equal to 1. So 1 will be less than 2. So in this case, your v will be equal to 0. Means that in this case is correct because it's the same. So we just fed the second sample. So will be 0 1. Let's say I put a different color here, 0 1. So 0 1 means that this will be 0. So this is will be equal to 0.6. You have a 1.6 here. So 1.6 will be less than 2. So for this particular case, the output will be still equal to 0. So since it will be the same, so it will be correct. So we move on to the third sample. We just put 1 0. So let's say 1 0. So 1 0 means that this is 0.6, this is 1, so we have 1.6. 1.6 will be less than 2. So for this case, v will be equal to 0. So it is correct. And then finally, for the final sample, which is the 1 1. 1 1, this is 0.6, 0 plus 0.6 plus 1, we have 2.6, 2.6, 2.2. So 2.2 will be higher than 2. So in this case, it will be higher. So it is correct. So we can say that the accuracy of the training will be 100% based on this value. So this is some sort of the process on how we can use the analytical method in order to fine tune, or in order to determine what is the optimal value of the neuron structures to ensure that it can converge with respect to the given input sample. So this is some sort of the example of the solution. So in this case, for this particular case, we select the different value, which is in this case b equal 0.5. So in our case previously, our calculation we used the 0.6. So this is also the correct answer. So this is the simple step, but I have shown you in details how we are able to obtain the value of this thing 0.5, 1, 1. So it's up to you. You can try that thing later on by using this type of the input value. So I left you with this type of the example. So I want you to do this type of example by your own. So we have different type of the data here. So we have 1 1 1 0 0 1 0 0. Okay, and then the output will be 0 1 1 1. So in this case, this is our model, in which for this model, the difference between our previous example that we don't have any bias. If you look at this particular example, we don't have any bias. So the question is that what is the value of W1 and W2 and also the theta here that can actually solve the given input data set here. So I left this thing as a quiz for you to answer that thing. So please submit your answer by next week in the given Google form. So the next part. So in some situation, if we try to solve the analytical method for the XOR problem, so this is the XOR problem. So XOR problem, exclusive OR problem. So for this case, if I try to plot the scatter plot for this type of the sample, so let's say x2 will be y-axis and then x1 will be the x-axis. So the same thing, value here is 0 and then 1, this thing will be 1. So if I try to plot the exclusive or sample for this thing in the scatter plot, let me change the color first. Okay. So for the first sample 0, 0, 0, so it will be 0 here. So the same thing, the second sample 0, 1, 1. So x1 is 0, x2 is 1. This thing will be 1. I just put x that represent 1. Third example, x1 will be 1 and then x2 will be 0. So this is the third sample and then this is the final sample 1, 1. So 1, 1 for this case will be equal to 0. So this is 0. So one of the things that you should note that XOR is actually the nonlinear problem. So why it is nonlinear? Because you need at least 2 straight lines in order to solve this particular problem. If you only have just single line, so it will be from the theoretical perspective, it will be quite impossible for you to determine the optimal solution. So the highest you can get for one cluster for the clustering problem maybe around 75% based on the given type of sample. So if we try to find the constraint function for this particular problem, so let's say if we select the value of the theta will be equal to 2. So this is all the 4 type of the constraint function. So for this type of constraint function, let's say b will be less than 2. Let's say I just put b will be equal to 1.5. Okay, this is for the first sample. Then w2 plus b must be higher than 2. So since we select b will be 1.5, let's say I just put the value of 1 here because 1 plus 1.5 will be higher than 2. So the same thing for w1, since this is 1.5, I just put it here 1. So 1 plus 1.5 will be higher than 2. So we're able to fulfill the first, second, and then third constraint function. And then we move on to the final constraint function, which is w1 plus w2 plus b must less than 2. So we have the value of w1 will be, which is equal to 1, w2 is equal to 1, and then also b will be 1.5. So we sum up everything here. So the value is actually higher than 2 instead of the lower than 2. So you can try to tune the value. Let's say you decrease the value of w, decrease the value of b. More or less, you can fulfill the constraint function number 4. So that's one of the reasons that I stated for this particular case. You can get the highest performance will be 75%, and it will be almost, or it is impossible actually to solve this problem by using the single neuron. So in the subsequent chapters, multi-layer perceptron, I will recap back this particular problem so that I will show you how we can use the multi-layer or combination of the multiple neuron in order to solve this problem. But for the time being, we just focus on the linear type of the problem. So one of the things regarding the analytical method is that it is practically applicable only for the simple perceptron with a small number of input. So let's say previous example we have only 4. So let's say if we have, let's say, 20 input, so we have the 20 constraint function. So it will be quite hard to tune or to configure the value or to find the optimal value of w and b to solve the particular problem. So in the situation that we have the many numbers of input, let's say 20, 10, and etc., we can use the iterative learning rule, which is we can use the Hebbian, perceptron, and the adaptive linear element, which will be covered up in our next chapter. So for this type of the chapter, so I will cover up until the analytical part for this week. So in the following weeks, I will cover all these three algorithms: the Hebbian, the perceptron, and the adaptive linear element. How we can configure, how we can perform the iterative training in order to solve the linear problem. So that's all for my first part of the lecture. Thank you very much.